All right. Welcome back to another lecture. In this section, 3.8, we're going to discuss the one-way ANOVA. And this is the test that we use if we're trying to compare three or more means. Okay? So the word ANOVA is a shorthand word for analysis of variance. And it's kind of an interesting name for a test when we're comparing means. We'll talk about that in a second. But the ANOVA test is similar to a homogeneity of proportions test, which we just learned about in 3.7. It's similar because the null hypothesis for the ANOVA is that all of the means are equal to one another. So it's not a test where we're saying mu1 equals 7, mu2 equals 13, mu3 equals something else. No, we're just going to say mu1 equals mu2 equals mu3, etc. for however many means we're comparing. So in that sense, we could call this test a homogeneity of means test, but the word for it is ANOVA. There are one-way ANOVA tests and two-way ANOVA tests. A one-way ANOVA measures the influence of one explanatory variable on one response. A two-way ANOVA measures the influence of two explanatory variables on one response. So for example, if you wanted to know what effect does exercise have on weight loss, you would run a one-way ANOVA, one explanatory variable, exercise, and one response, weight loss. But if you wanted to know what does the effect of diet and exercise together have on weight loss, then you would run a two-way ANOVA. You would have two explanatory variables, diet and exercise, and then one response, right? But the two-way ANOVA is beyond the scope of this course. Okay, we're not going to get that far. We're just going to stick with a one-way ANOVA. You may wonder though, like, well, what if you have more than two explanatory variables, okay, multiple explanatory variables, and what if you have multiple response variables? Like maybe you want to test how diet, exercise, and sleep affects weight loss, or how diet, exercise, and sleep affect weight loss and mood, right? So then you could have like three explanatory variables and two responses or something. For those kinds of situations, we could run a test called a MANOVA or an ANCOVA. Okay, so this is like a multiple analysis of variance, and this is an analysis of covariance. But those tests are also beyond the scope of this course. We're just going to stick with the one-way ANOVA. Regarding the name analysis of variance, as I mentioned a second ago, it's kind of an interesting name considering that what we're trying to compare here are means. So why do we compare the variances? Well, the basic idea is that if there's only a little bit of variability within one sample compared to a lot of variability between the samples, then that would indicate that the data are nicely separated into distinct groups, okay, which would indicate that each of the samples comes from populations with different means, okay? There are the details of that can be found here. So if you're interested, you can look at it. You could look at that. But without further ado, let's just get into it, okay? So here are the steps for running the ANOVA test. This is, again, a test for comparing three or more means. In Art of Stat, to get the p-value, we're going to use the ANOVA one-way app. And then everything else is the same. Conditions to check, well, we have to have k independent random samples. The populations have to be normally distributed. So usually the problem will just tell you so, or if it gives you data, you can look at some histograms and kind of verify that they're normally distributed. And then 3, the populations have to have the same variance. We'll assume that that's true as long as the largest sample standard deviation is no more than twice the smallest sample standard deviation. Again, this is not going to be a major emphasis of the course, but just so that you're aware, these are the conditions that would have to hold in order for the results of an ANOVA to be considered valid. Okay, let's look at, I just want to take you through 2 examples. And by the way, there is data for this. So there should be a data set with the notes for this lecture so that you can just copy and paste. Anyway, so it says the data below show the shear bond strength for different repair kits for chipped porcelain measured in megapascals. A sample of 20 porcelain specimens was taken and the bond strength measured. Part A says use Art of Stat to calculate the sample mean for each repair kit and create a side-by-side box plot. What do you predict the outcome of the ANOVA to be? Okay, Well, let's call these groups 1, 2, 3, and 4. And what I'm being asked to do in part A is to compute x bar sub 1, x bar sub 2, etc. And it says that we can use art of stat to do this. So let's do it. I'm going to copy and paste the data here. And then I'm going to open up art of stat. Now, it's been a while since we've used these apps, but if I want to make like a side-by-side box plot or something, then I can use the Explore Quantitative Data app. And I have several groups that I want to compare. So let me do my own. And we have 4 groups in total, so I'm going to change the number of groups to 4. Okay, so then once I do that, I have a place to put in each of the data sets, right? So I'm going to paste the data for group 1. And let me go grab the rest of the data. Okay. So once I've done all that, I get all of these really nice summary statistics as well as this side-by-side box plot. If I wanted to, I could change the group labels. So instead of calling them group 1, group 2, group 3, group 4, I could call them Cojet and Sillistor and all of those different names. But I'm just going to leave these group names for now. What I notice is that, well, I get all the sample means here, so I'll write those down. But then I also notice that I get this really nice grouping where it looks like groups 3 and 4 have a pretty similar looking, mean. And groups 1 and 2 also have a pretty similar looking mean, but there's this pretty wide gap between the bottom 2 and the top 2. So I would say that probably group 1 and group 2 have a larger mean than group 3 and group 4. I would guess that we will most likely reject the null hypothesis because of that difference that we're seeing there. But there's only one way to find out, and that's to actually run the test. But let's go back and write down these results. Okay, and you can even see in the sample means themselves that there's this pretty large gap between Cojet and Sillistor up top, and then Samara and Ceramic Repair on bottom. So, yeah, my prediction is we'll reject the null. Okay, but to see if we do, we'll run the test. Okay, so step 1, state the hypotheses. The null hypothesis is that actually there's no difference in any of these groups, right? They're all the same. The alternative is that at least one mean is different than the others. Okay, step 2 is to calculate the sample means, which we've actually already done in part A, so I'm just going to draw an arrow to it so I don't have to rewrite that step. And then step 3 is to compute the p-value. We're going to go to the ANOVA one-way app, and then we're going to enter the data, which again we can just copy and paste over from that Excel workbook, and then we'll get a nice p-value from that. So let's head over to the ANOVA one-way app. So I'm going to leave this one. And the ANOVA one-way app is almost all the way at the bottom. It's down here next to the chi-squared test that we were using in 3.7, right? So the ANOVA one-way is right here. Okay, and I don't want to do this example from the textbook. I have my own data. I don't have 3 groups, I have 4 groups, so I'll change that to 4. And then again, I'm going to have to copy and paste the data into these boxes, okay? I can change the group labels over here if I want to, but I'm okay with just leaving them as is for now. So let's copy and paste the data. Okay, once you get all the data in there, it'll automatically calculate the p-value. It also calculates a whole bunch of other stuff that we're not going to really get into. It also calculates the sample means again. So instead of doing all of that work in the Explore Quantitative Data app, you could just do it here since it's going to calculate those sample means for you anyway. It gives you this side-by-side dot plot. If you would rather have a box plot, you can change the type of plot to box plot over here. And then it gives you the same box plots that we saw earlier. Actually, they're not the same. So I think there might be a slight difference in the way that this app computes the fences and so forth than the way the other app did. But that's okay. I do like how they have the means, or how they show the means down here for each of the groups. So again, you can see that the mean for these two is pretty close. The mean for these two is pretty close, but there's a wide gulf between them, which is why, most likely, that's why we're rejecting the null hypothesis. Okay, we got a very small p-value. So let's head back over to our notes and write down our p-value, 0.0023. Okay, so 0.0023 is less than 0.05. So reject H null. We're rejecting H null in favor of the alternative. That means at least one of the means is different. In the context of this problem, we're talking about the bond strength of the different repair kits. So in conclusion, we might say something like, there is sufficient evidence to conclude that at least one of the repair kits has a different mean bond strength than the others. Okay. Now, Part C asks us to do a little follow-up. It says, in the web app, click on pairwise comparisons and confidence intervals, and then interpret what you see. Okay, so let's head back over to the web app. Okay, so back here in the web app, we're going to click on this little button down here that says pairwise comparisons and confidence intervals. And what that does is it gives you this big chart, okay, which gives you some confidence intervals, and it also gives you p-values. Okay, so what this is doing is it's doing pairwise comparisons. It's comparing, like up here in the ANOVA, we were comparing all four groups at the same time. What this is doing is it's comparing group 1 versus group 2, group 1 versus group 3, group 1 versus group 4, right? 2 versus 3, 2 versus 4, and then 3 versus 4. So it's doing all of the individual side-by-side comparisons. So it's kind of interesting. And then you can look at the p-value of each of these, right? You can say, well, when we just compare group 1 and group 2, we get a large p-value. Do not reject the null. There's no difference between group 1 and group 2. When we compare group 1 and group 3, we do find a difference. Okay, and when we compare group 1 and group 4, we do find a difference. 2 and 3, 2 and 4, we find a difference there. But when we compare 3 and 4, we find no difference. Okay. You can see all of that down here. Any interval that contains 0 is an interval where there's no difference in the two groups that you're comparing, okay? Because if 0 were in the interval, and we've talked about this before, right? But if 0 is in the interval, then that means mu1 minus mu2 might be equal to 0, which means that mu1 and mu2 are not are the same, right? They're not different at all. So any interval that contains 0, you would not reject the null hypothesis, okay? And so you can see that there are two intervals where we wouldn't reject the null, and that's when we compare 1 and 2, and when we compare 3 and 4. So 1 and 2 are probably the same, 3 and 4 are probably the same, but all other group comparisons are finding a difference, okay? This falls in line perfectly with the box plots that we were looking at. Let me change this to a box plot again. This falls in line perfectly, right? Groups 3 and 4 are the same. Groups 1 and 2 are the same, but there's a wide gulf between them, just like we predicted, okay? So what's it asking us to do in Part C? Click on pairwise, interpret what you see. Well, the pairwise comparisons indicate that groups 1 and 2, that's cojet and Sillistor. So they indicate that cojet and Sillistor have a similar mean. And the groups 3 and 4, that's Samara and ceramic repair. Okay. I don't know if I'm saying these names right, by the way, but and ceramic repair have a similar mean. But there's a wide gap between those two blocks, between those two groups. Okay, so if you were asked a follow-up question like, which repair kit would you, would you recommend to a friend? I think we would say either cojet or Sillistor, because they have a larger shear bond strength. They're pretty comparable to one another, so you could go with either one of those and steer clear of the other ones. Okay. Let's look at a second example. An obstetrician knew that there were more live births during the week than on weekends. She wanted to determine whether the mean number of births was the same for each of the 5 days of the week. Okay, so she already knows there are more live births during the week than on the weekends. But what about if you just look during the week? Is there a difference in the number of live births during those days? Well, she randomly selected 8 days for each of the 5 days of the week, Monday through Friday, and obtained this data. So part A says to test the hypothesis of equal means at the 0.01 level of significance. This time we're going to be comparing 5 means, right? The mean for Monday, Tuesday, Wednesday, Thursday, and Friday. I'll let you go ahead and pause the video and write down your hypotheses. Okay, so you should have something like this for your null and alternative hypotheses. All of the means, the null hypothesis is that all of the means are the same, right? There's no difference in the number of births during the week. Now, step 2 is to compute the sample means for each of those days. If I were you, what I would do is I would just compute those sample means using the ANOVA app, since you're gonna have to do that to do step 3 anyway. But so that's my advice. But I'll let you pause the video and go ahead and compute those. Okay, so here's what I'm getting from the one-way ANOVA app. I changed it to 5 groups, and then I just copied and pasted the data from Monday, Tuesday, Wednesday, Thursday, Friday. You can change these names if you want, but it's not necessary, right? Monday. We can also look at a box plot, a side-by-side box plot instead of the dot plots. I just think it's easier for me to make sense of. Yeah, because visually, it's like, oh, wow. Monday has far less live births than the other days, right? Wednesday is maybe a little bit less than the other groups, and Tuesday is maybe a little bit more than the other groups, I guess, but Monday is the clear outlier. There are very few live births on Monday, which is interesting. Anyway, we get a very small p-value here, less than 0.0001. That indicates, of course, that we're going to be rejecting the null hypothesis, which means we can safely conclude that at least one of the groups is different. And I would say Monday is a clear bet for what's different here. If we wanted to see if Tuesday maybe had a little bit more than the others, I mean, obviously it does in this data set, but if we wanted to see if that was a statistically significant difference, then we could click on pairwise comparisons. And so notice it's doing Monday versus Tuesday, Wednesday, Thursday, Friday, and then Tuesday versus Wednesday, Thursday, Friday, and then Wednesday versus Thursday and Friday, and then finally Thursday versus Friday. So the ones where differences are being detected are these ones down here: Monday versus Friday, Monday versus Wednesday, Monday versus Tuesday. Oh, hold on. This is kind of hard to read, huh? Am I getting this right? This one is Monday versus Wednesday, Monday versus Tuesday, Monday versus Thursday, and Monday versus Friday. So it's like Monday versus every other day of the week. So Monday is the different one. None of the other comparisons are detecting much of a difference, right? So Monday is the only day that's really significantly different from the rest. Okay. Anyway, so let's head back and write down these results. Okay, these are the sample means that I got from ARTIFSTAT. And then for the p-value, of course, I went to ANOVA, one way, entered the data, and got a p-value less than 0.0001. So, since 0.0001 is less than 0.01, we reject H null. Okay, so go ahead and pause the video and see if you can write down a conclusion. Okay, so your conclusion should say something like, there's sufficient evidence to conclude that at least one day of the week has a different mean number of live births than the rest. We're not, the test itself doesn't tell us which day is different from the rest, but you could look at those side-by-side box plots that we saw in ARTIFSTAT. You could also just look at step 2, and you can notice that, oh yeah, 10,696 is quite a bit less than all the rest of these, right? So that seems to be where the difference lies. Part B, what does the p-value measure in this scenario? Well, the p-value measures in this scenario the same thing it does everywhere else. It's the probability of obtaining the sample results that we obtained if we assume the null hypothesis is true. So we would say there's almost a 0% chance, because our p-value was less than 0.0001, right? So there's almost a 0% chance that we would obtain the sample results that we obtained, or the sample means that we obtained, if, in fact, the number of live births were the same on each day, as the null hypothesis suggests. Okay, there would be almost a 0% chance of us seeing what we saw, which means, well, maybe it's not such a good assumption to make. Maybe we should reject that assumption, right? And so we do. We reject the null hypothesis. Part C, do any days stand out as having a significantly different number of live births? What might account for this? Well, yes. Monday had far fewer births than the other days. Okay, what might account for this? Well, I'll let you think about that. So go ahead and give the video a pause and give your answer to that. What do you think would account for Monday having fewer live births than the other days? Here's my answer to the question. I would just, and I'm not going to write this down, but I would encourage you to write something down. But what I would say is sometimes students think, well, because people hate Mondays, right? And I don't know if that's such a good answer, because it's not like the baby knows what day of the week it is. So the baby's not just going to say, oh, I hate Mondays, I'm going to stay inside today, right? Now, I suppose you can make an argument that, well, no, but the mother hates Mondays, and that sends some kind of like chemical signal to the baby, like don't come today or something like that. I suppose that could be part of what's going on here, but I doubt it. I don't think that that's really what's happening. I think that what's happening is that there are certain kinds of births that can be scheduled, like cesarean sections, for example, or also sometimes women are induced, right? So the doctor will give them a medication to get their labor started. So if the baby has just been like if the baby is really late, or if the mom is having a lot of health complications and needs to give birth, right? The doctors might schedule ahead of time. They might schedule when they're going to induce labor or when they're going to perform a cesarean section. Well, so that means if a doctor doesn't want to come in to deliver a baby on Monday, they're not going to schedule the induction of labor or the cesarean section for a Monday. They'll schedule it for another day of the week. And that's probably why you see a slight decrease, a slight drop in the number of live births on Mondays. So anyway, kind of interesting, but that's what I would say about that example. So this is how ANOVAs go. I just want to give a quick summary of the tests that we've talked about for means. We gave a little summary about the tests for proportions at the end of 3.7. So here's a little bit of a summary about the tests for the means that we've talked about. So we've talked about a one sample t-test. Okay, we did that from sections 3.2 to 3.4. Okay, and then we talked about two different kinds of tests if you're going to be comparing two means. One of them was the two sample t-test, and that was for independent sampling. And then another one was the matched pairs t-test, and that was for dependent sampling. Okay, so if you want to do a test where you're only looking at one group, well, you run a one sample t-test. If you want to do a test where you're comparing two groups, well, then you're going to have to decide, okay, are the samples independent or dependent? Okay. And then finally, if you want to run a test where you are comparing more than two means, then you would run the ANOVA that we talked about in this section. So in order to know when to use a two sample t versus a matched pairs t, we just have to decide if the samples are independent or dependent. And just as a reminder of how that works, right? With independent samples, the idea is that there are no matched pairs. You're not linking up the individuals from one sample to the individuals in another sample in any way, okay? The samples are obtained independently of each other. With dependent samples, you do have those links, right? You have matched pairs. So that's how you know how to distinguish between a two sample t or a matched pairs t. The ANOVA test is similar to the homogeneity of proportions test. We talked at the beginning of the lecture about how instead of calling it an ANOVA test, we might call it a homogeneity of means test, right? That would be a good name for this test. We don't have an analog for the goodness of fit test for means. As far as I'm aware, there's no test that exists that will allow you to test mu1 equals number, mu2 equals some other number. I don't think that we have a test for that. I could be wrong, but if we do have a test for it, it's not something that's covered in this class, so you won't have to worry about it. And that'll do it for the one-way ANOVA.